All right, we're going to get into chapter 17, part 2. We're going to talk a little bit about the structure of benzene. The structure itself, the way that the atoms are put together, was figured out in 1866 by Kekulé, and he made one major mistake. All right, and so let's take a look at the image here. Can you tell just by looking what that mistake was? This is an equilibrium arrow. He didn't understand the idea of resonance yet. The double bonds in the benzene ring are alternating as you go from the left to the right structure. And that is, as we know now, that's a limitation of Lewis structures and bond line structure. The double bonds aren't actually changing places. The real structure lies somewhere in the middle, right? All of the carbon-carbon bond lengths are the same length. So in reality, each carbon-carbon bond is sort of like a 1.5 bond. So you might see benzene drawn this way to show that those 3 pi bonds are shared throughout the ring. Another really common way to write that is with a circle in the middle. Now, it's okay to write benzene this way. It's a little bit faster, but not in a mechanism that involves benzene itself. If we're actually dealing with a hydrogen in one of these double bonds, then it needs to be drawn with one of the resonance structures. But this is this right here, very common way to represent benzene. Now, the reactivity of benzene is very different than you see with alkenes or dienes, even conjugated dienes. The reactions that we learned back in Organic 1, like bromination, all these different electrophilic additions, they don't happen with benzene, right? Nothing happens. So we're going to investigate why that is. There is a stability about this type of conjugation that you don't see in isolated alkenes or even simple conjugated dienes. We see that stability when we look at hydrogenation reactions. If we look at cyclohexene, right, there's a certain amount of energy that is released upon hydrogenation. When we look at cyclohexadiene here, it's not quite double, but we now understand that's because conjugation gives a little bit of stability, right? So a conjugated diene is not, it has lower energy than 2 isolated alkenes. Where if you were just extrapolating upon this number here, how much energy was released upon the hydrogenation of one double bond, you might expect it to be 3 times that amount for 3 double bonds. But it is far, far less than that. In fact, it's even lower in energy than the conjugated diene. So something special is going on here, something stabilizing, something more stabilizing than conjugation alone. When we look at the pi bonds in a benzene ring, right, you have 6 p orbitals that all can overlap. They're all close enough to overlap. So you get this overlapping ring of electrons where all of the electrons can spread out. If you can spread electrons out, that's going to add stability. When we look at the molecular orbital theory diagram, what we wind up looking at, we're just focusing on those pi electrons. Remember, there's 1, 2, 3, 4, 5, 6 p orbitals. So we're going to wind up with 1, 2, 3, 4, 5, 6 molecular orbitals. You are going to have overlap in a way that is lower in energy. The lowest, of course, is everything is in phase. Then you are going to have one node options. So there winds up being two bonding orbitals that are a little higher in energy, but they are the same in energy with each other. You wind up with two anti-bonding orbitals of the same energy and an anti-bonding orbital that is the most or highest in energy, where everything creates a node, nothing overlaps. This is also called a frost circle. We are going to talk about this throughout this lecture. But essentially, you're taking the ring, and if you think about the points in the ring, that's how many orbitals we're going to have. So there are 6 points, and essentially here I've drawn a hexagon, but with little orbital lines. Now, how many pi electrons are in benzene? 6, right? 3 pi bonds, so 6 pi electrons. We have bonding below the half line and anti-bonding above. You have energy increasing on the y-axis. If I am going to if I'm going to fill in this molecular orbital chart, well, at the beginning I start, with my off-ball principle and Pauli. I know that I can put 2 electrons in that lowest energy orbital. But Hund's rule is also going to be important when we get to these degenerate or equal energy orbitals. So 1 and 2 went in the first orbital, 3, 4, 5, and 6. Now, even though it doesn't seem like it matters here, it is important to think about Hund's rule. It will be important in a future problem. But what we can see is because everything can overlap, all 6 pi electrons wind up in lower energy bonding orbitals, making this a very stable structure. And just slides with what we were talking about. Now, if this creates such a stable structure, then why don't we see similar stability when we look at cyclobutadiene and cyclooctatetraene? When we try to do these reactions, for one, if we just use Br2, which won't react with benzene, it will react with cyclooctatetraene. In fact, it reacts just like as if those double bonds were isolated. Cyclobutadiene is so reactive that it will react with itself before you ever even could add bromine. And so what you're seeing is very unstable. This is stable, but it doesn't have increased aromatic stability. And how can we reconcile this? In so many ways, they're very similar to a benzene ring. Well, we're going to take a look at something called Huckel's rule. And I'm going to, let's start here. There are 3 options. Something can be aromatic, anti-aromatic, or non-aromatic. And so we're going to develop some rules here. So, we're going to look at our 2 rules and see how we can determine which of these 3 categories a compound falls into. So, our rules for aromaticity. Number 1, you have to have a fully conjugated ring with overlapping p orbitals. That's the main thing you want to take away. You have to have a ring of overlapping p orbitals. Number 2, Huckel's rule tells us we must have an odd number of electron pairs, right? Specifically in that pi cloud. Now, if you've got a different book, if you've taken this class before, even if you're reading through this book, a lot of times this is called this 4n+2 rule. So, for instance, when we think about benzene, right? There are 6 pi electrons. Well, that fits into 4 times 1 plus 2. Whereas we have 8 electrons here, there is not a whole number that would satisfy that. I don't think that is the easiest way to understand Rule 2. I stick with this. If you have an odd number of electron pairs, it's necessary to be aromatic. So, for instance, benzene has 3 pairs of pi electrons. That's odd. Cyclooctatetraene has 4. That's even. And then 2 for cyclobutadiene, even again. All right, so to be aromatic, both 1 and 2 must be true. To be anti-aromatic, it's going to be 1 is true, 2 is false. So you have that conjugated ring of overlapping p orbitals, but an even number of electron pairs. And that's going to help us to understand 2 and 4 in a moment. And then what is non-aromatic? 1 is false, or 1 fails. Right? It doesn't matter how many pairs of pi electrons. If it's not fully conjugated ring, or it's not a ring of all continuous overlapping p orbitals, it's can't be aromatic at all, or anti-aromatic. So things like sp3 carbons break that up. So for instance, if we looked at this, we have some double bonds, but we have some CH2s in here, right? This cannot be a fully conjugated system. It can't have a complete overlapping of p orbitals. And so this one would just be non-aromatic. Now, to look into the explanation of this a little bit further, using these frost circles, using these molecular orbital diagrams, you can see why cyclobutadiene is so unstable, even more so than just because it's a 4-membered ring. When we look at those molecular orbitals, we're going to take however many points, and that's how many molecular orbitals. You always have one that's lowest in energy, because that's where everything is in phase. Then the next 2 are the same energy, and you keep going up in pairs unless you run out, and then it's just 1. Here we have 4. What's interesting about this one, we haven't seen this before. You have bonding that's lower in energy than the original atomic orbitals. You have anti-bonding, but you wind up with some orbitals that are equal in energy to the atomic orbitals. And those are considered non-bonding. Doesn't make things better, doesn't make things worse. What's really interesting here, though, is there are 4 pi electrons. And if we fill this in using our Pauli, Aufbau, and Hund rules, we wind up with a set of unpaired electrons. This is the key to something being anti-aromatic, right? This is what makes it so this is one of the things that makes it so unstable. So, if that's the case, why is cyclooctatetraene stable? Maybe not as stable as an aromatic compound, but way more stable than what we see with cyclobutadiene. So I'm going to draw this again. We have 1, 2, 3, 4, 5, 6, 7, and 8. And draw that line through the middle. You've got bonding down here, you've got anti-bonding above, and you have non-bonding on the line. Let's make sure those are clear. You have 8 pi electrons in this example. So it's going to be 1, 2, 3, 4, 5, 6, 7, and 8. You have unpaired electrons that aren't even in lower energy orbitals. So it should be anti-aromatic. And I'm going to explain to you why I would expect you to tell me that it's anti-aromatic. One of the rules for being aromatic is to have a fully conjugated ring with overlapping p orbitals. Well, that only happens if this is flat, if your cyclooctatetraene is planar. But because being anti-aromatic is so unfavorable, it's so high energy, because cyclooctatetraene is a bit bigger, it can fold. Now, once it folds, you do not have a fully conjugated ring anymore. It's broken, right? We break that cyclic pi system. So it will be anti-aromatic if it was planar. But we see that it has reactivity like it's an isolated alkene because it bends, right? It breaks that conjugation. It breaks that overlap of p orbitals. When I ask you to identify aromaticity, I'm going to ask you to assume that it's planar, because that way I can see how you can apply these two rules. Assuming it's planar, if possible, is it fully conjugated? For instance, in this example, this one, it's not possible to be planar. This carbon here is sp3 hybridized. It's tetrahedral. It's 4 sigma bonds. You can't change that. So it's non-aromatic. This guy, all double bonds conjugated to one another, could be planar, right, without breaking any atoms off. So if this one were planar, it would be anti-aromatic. You can explain reactivity that you see in real life, though, by taking into account that it can fold. Now, if you are having any trouble with drawing these frost circles for different ring sizes, there is some notes here. So you can pause, take some notes. I don't ever draw the circle or the polygon, but if that helps you, by all means, do it. Slide 27 here. You can come back to that. You have an example of the frost circles for everything from a 4-membered ring to a 10-membered ring. You note that the bonding orbitals, there's always an odd number. So if something is aromatic, right, all of those electrons are going to be in that green box. If it is anti-aromatic, often it'll sneak up out of that box. This is just going over what we have been saying, right? Aromatic, anti-aromatic, non-aromatic. If you just want some different words as you're learning, this slide is for you. Other aromatic compounds. There are lots of other aromatic compounds, and most of those we're going to explore in part 3. I do want to finish up here talking about annulenes. This is really just a little addition to the nomenclature. Annulenes are just fully conjugated rings. Right, and it gives you an alternative way to name them. So like benzene would be 6-annulene. So what you put in here is your number of pi electrons, and then you just say annulene, right? If I have 6-annulene, I know that that means I have 6 pi electrons, so that's 3 double bonds. For it to be fully conjugated, it's got to be a 6-membered ring. Annulenes can be aromatic, anti-aromatic, and even, which may seem non-intuitive, non-aromatic, right? By nature, they should follow rule 1, that fully conjugated ring, right? There is a p orbital on all of these carbons. But just like cyclooctatetraene in real life, something like 14-annulene has hydrogens in here that are all super close. So this winds up bending a little bit to get those hydrogens a little further away from each other, which breaks that conjugation. So it is possible for them to fall in any of the categories. I'm not going to ask you about questions like that, but it is good for you to know the term annulene. All right, in the next video, we will get into aromatic ions and aromatic heterocycles.